Okay, hello everyone, good morning. My name is Adrian, and I defended my PhD in September, so now I'm a research associate working on the Detour Lake deposit, but here to basically provide a summary of the PhD. So I have to apologize if some of the details are missing, but I'm going to try and get through all the main themes of the PhD and see how it relates to the Metal Earth project. So my project is part of the gold fluid window thematic project, and we're looking at kind of the genesis of orogenic gold deposits in the Archean. So we know that orogenic gold deposits are distributed across Earth's history, right? And they tend to share similar characteristics, regional lithological boundaries, typically at the green schist amphibole transition, and defined in general by quartz carbonate with tourmaline and lower sulfide content than other deposits typically. And so metamorphic devolatilization has kind of emerged as the main player in sourcing these metals and fluids. And I won't get into maybe all the reasons why, but one thing we know, and the metamorphic devolatilization model is primarily based on Phanerozoic rocks initially, and for Archean rocks, it's been proposed that they're from the devolatilization of mafic rocks. But in general, the Archean crust we know varies quite a bit from the Phanerozoic in its composition and structure. Kind of the metamorphic evolution of Archean supercrustals, I would say, is generally a bit underdeveloped, especially the relation between temperature, pressure, and composition. So it's really hard to have a complete model without knowing these, the structure of the crust, the isograds, and the relationship between composition, temperature, etc. So what are these factors? How could they contribute to differential gold endowment? And so my goal was to look at the sediments in the Quetico subprovince. And so the Archean metamorphic devolatilization model has been in the past based on, like I said, the hydrated mafics model, but a lot of the work shown by Ian Pitcairn and Diogo Ribeiro from our group has shown that you can track the isograds much better in the metamorphic terrains or the metasedimentary terrains, and you can track that you lose gold through those isograds a lot easier than you can, at least in the mafic domains. And it's a lot easier to handle any sort of PT estimates in the metasediments versus volcanic. So the Quetico is a great opportunity to look at basically a complete and symmetrical gradient through the chlorite low-grade margins in through the granulate core, and then back on the other side into the low-grade margins. And it's a huge belt, very well exposed with highways. And its margins are variably endowed with gold. So most of the gold in the area is going to be in the Beardmore-Geraldton belt, whereas the western margin in the Thunder Bay area is going to be typically devoid of any major deposits. So the scope here is to go from the big scale all the way down to the micro scale, and to really base everything in petrology and petrochemistry. And so in this, I had three main questions that I wanted to address for the Quetico specifically. What is the stratigraphic setting and architecture of the belt? Are we dealing with a prism? Are we dealing with an extensional basin? What is the architecture of it? And so that's mostly done through compilation mapping. And so the second question was, what are the pressure temperature conditions for fluid production and gold release? So we know from Diogo's work and on those before that the gold in the sedimentary subprovinces is initially in the pyrite 1, and it does, as pyrite is consumed upgrade, you also lose gold in the rock, not just in the sulfides, but in the whole rock measurements. So what are the conditions for that sulfide and fluid release? So, and then the last one is, can we place timing constraints on all these events? And I'm doing that with cesium, hafnium, and monazite, uranium monazite chronology. So the first step was to do a new compilation map essentially of the Quetico, and so there isn't really like an assemblage map available for the Quetico or most of the Western Superior. So I kind of attempted to do an assemblage level compilation map, and then basically look at different ways geospatial analysis to characterize it, the structure of the belt and the stratigraphic structure. So kind of the main key points is that the assemblages seem to vary symmetrically along the north-south axes. So you're finding kind of in general that you have similar composition and similar ages and proportions of those stratigraphic assemblages on the north and south sides of the belt. Into the Quetico proper, you get similar contributions of mafic volcanics panels or interleaves, and then in the center, of course, it's going to be mostly sediments and granulates or intrusions. If you take the whole area of the Quetico and you assume a minimum paleo depth of 10 kilometers, which I think is pretty as a low ball really, because we're dealing with some pretty hot rocks. Making that calculation is about 300,000 cubic kilometers of sediments, which is a lot. And that's just, so for instance, a modern prism with maximum, the same strike length and kind of maximum reported thicknesses would be no more than 100,000 kilometers cubed. So I think we're on a different scale that a prism is capable of handling that much sediment. Other observations that lean into this is that we looked at the both margins, especially the contact areas, where you have this interleaving of mafic and sedimentary units. To the north, this is like in the Beardmore-Geraldton area, these contacts are mainly characterized by transcurrent shear zones, although I would say probably not everywhere. There was no change in the metamorphic or structural character across these contacts. So it becomes difficult to see those, to me, as major suture zones or thrusts. To the south, very similar relationships are observed in this case, or in a less structural domain, and you can actually see that these are primary contacts. So the idea is that either it's conformable interlayering like we have in the Pontiac, or it's potentially also an isoclinally folded unconformity. Both seem to be valid. So then I did a compilation of the structure. The key points here are that the dip is basically consistently subvertical. At the margins, it's subvertical. And then as you go through all the high-grade zones into the OPX zone, it's like 90 degrees dip. So you're not really getting the typical flattening within those high-grade zones that you see in basically modern metamorphic terrains. So that was a bit of a puzzler. At the margins, you get a lot. It's kind of described as these F1 axe folds, which are very cryptic, but you can see reversals in the Younging direction. So I compiled all the Younging directions that have been reported, and you can see these rose diagrams show that to the north, you generally have a northern Younging, and then to the south you generally have a southern Younging, although there is some variability due to that F1, those really tight F1 folds. So this could be described in general as an upright anticlinorium, and there seems to be a shallow eastward plunge to it. The metamorphic isograds, here we focused a lot on the isograd mapping. It was defined by the first appearance of metamorphic minerals in any clastic sedimentary protolith. So there is a little bit of variability in the protolith composition, which I'll talk about, but in general, we have this symmetrical distribution from chlorite zone, as I mentioned, through biotite garnet. Storolite and andalusite seem to be in the same rocks, if you have the right chemistry. Cordierite, sillimanite, in situ melt appears after the sillimanite zone, and then if you increase grade beyond that, you get K-feldspar and then orthopyroxene. So that is, it's not a complete sequence everywhere, but that's the general sequence for the Quetico. The lower grade isograds are very tightly spaced, which has been like pretty unrealistic gradients. So you would probably have to do something to tighten those post in a later process. In the center of the Quetico, though, the gradients become much more spaced out, or the isograds become much more spaced out. And they all appear to be at least slightly discordant to the main stratigraphy. So these volcanic margins here, you can see that they don't really, they kind of leisurely cross those boundaries. And then plutons and major faults, they're also a bit discordant to those. So this is the sediment chemistry I was talking about. It's really key in metamorphic petrology to understand the compositional variability, because if you want to make inferences about the whole basin, you need to know what very subtle changes in chemistry can have on your PT predictions and on your phase relations. So the protolith variability here, you can see that there's actually a lot of calc semi-peelites and semi-peelites, probably 70 to 80% of the sediments would be characterized as that. And so you can see that the median worldwide peelite, calculated by Forshaw and Pattison, plots up here on this AFC diagram. So it's actually interesting that pretty much all of the sediments, even the peelites, are aluminum poor compared to our typical peelites. And that has very important ramifications for our phase relationships. I'll touch on that a bit later. The grade relations, we also track that. So using infrared spectrometry on carbon and sulfur, as well as H2O plus or H2O crystallization. And you can see that you get a main decrease from basically right at the biotite in. You get a drop in H2O, a sharp drop in carbon. Sulfur, though, is basically, there's no trend. So only layer-to-layer variability. So let's put that in a reaction sequence. I guess I won't spend too much time on this, but this kind of describes what we're expecting the reactions to do. If you take a rock from chloride zone, you get biotite in, you consume a bit of chlorite, you consume quite a bit of muscovite, and then K feldspar goes out. So you have some K feldspar clasts initially. And so that actually results in a big change in the volume of the rock, or the overall mineralogy of the rock. Then you get garnet in. Garnet, you only get 1%, 2%, 3% garnet. It doesn't really affect things that much. You consume any sort of muscovite that's left, epidote goes out there. Staurolite, andalusite at the same time, and then cordierite and silmonite. So this is all describing the subsolidus sequence. The carbonates and sulfides and oxides was a bit more interesting, I think. You get calcite that's first contained within kind of altered plagioclase clasts. Once you increase grade a little bit, these calcites you can see become discrete grains in the matrix, and then increase grade a little bit more, and then you just lose all the calcite in the rock. We didn't identify any graphite either. The pyrite, you get pyrite 1, which is a gold bearing, and then that's associated with rutile, and then that changes to basically pyrrhotite and ilmenite at biotite to staurolite zones. And then you get a second pyrite 2, which appears a bit later. It's most likely related to retrograde or melt processes. It's a bit unclear about this one. So for the phase equilibrium modeling, I first used the garnet, mineral chemistry, and the observed assemblage, and plotted and calculated in a system that's basically all the major oxides. And the point of this is to try and get the shape PT vectors to see, okay, get a sense of the PT path of these rocks. So this was done with isopleth crossing, and so you can see that basically the isopleths converge here at about 570 C and 6 kilobars. So, and interestingly, this appears to be about the peak conditions that we see, or the peak pressures that we see in the belts, in the garnet and staurolite zone. That seems to be where you preserve at least the 6 kilobar signature. And then once you increase the temperature, you're probably decreasing pressures as well as you're heating. So that 6 kilobar signal is overprinted. For the more relevant to the sulfide and fluid modeling is doing it at lower grades, because obviously that's where you have the initial the goods to make the fluid. And so The approach here was to then add sulfur, carbon, and fix the H2O, so that we can kind of do a forward modeling of what we think those fluids are gonna look like as we increase grade. So for the chloride zone, we're inferring an equilibrium assemblage at about 400 degrees C, 2.5 kilobars. You can't really be more precise than that because you don't have any other really controls like isopleths to work with. But the important thing is that you get a fluid pulse with, the main fluid pulse is at calcite out. So you can see that it follows this, that calcite isoline. And then you get H2S, so this is basically the sulfur in the fluid. And you can see that it increases steadily with T and lower P. So you're not actually getting a sulfur pulse really at during this pyrite to pyrrhotite transition. And I'll kind of explain why in a bit. So then the next step was to try and look at more realistic conditions where you basically fractionate the fluid out of the rock and calculate how much of that is fractionated and see what the phase relations do. So to do that, you need a PT path, and then so this is the PT path that I selected. It's informed by the garnet isopleths. And so I compared two protoliths from the low-grade zones, and you can see that this is the sequence of the reactions. In the semi-pelite protolith, the main fluid production, again, is happening at this muscovite, calcite, and chlorite out, and that produces a large volume of CO2-rich fluid. You'll notice that the H2S, the sulfur in the fluid, is very low. In the pelite protolith, you still get a bit of that first reaction at about 475, but you can see that because you have a bit more aluminum in the rock, you have a bit more potassium in the rock, you're not consuming as much of the muscovite, and so some of that remains to the staurolite zone. So you actually get two pulses in that rock. And the second pulse is actually just basically a pure H2O fluid. So why is this sulfur not going into the fluid? This has to do with the oxidation state, and because we're reacting the iron with that you get when you basically consume pyrite, that gets reacted with chlorite, let's say, some of the silicates, and then that's then in turn goes into the oxidation state, and so everything. It's really the pyrite to pyrrhotite stability is very sensitive to oxidation state because of that, and that's kind of that reaction kind of summarizes a bit why. And in kind of Phanerozoic rocks where you have graphite, you don't actually get this phenomenon because graphite doesn't have oxygen bonded to it, so the oxygen from that reaction then goes into the graphite to form CO2, I guess, and then that basically buffers that reaction. So in the absence of graphite, you get this really sensitive relationship between sulfide stability and oxygen. And the other point of this is that by increasing the sulfur, so I compared two different protoliths with different sulfur contents, and you can see that increasing the sulfur actually expands, in this case, the window of pyrite to pyrrhotite transition. Whereas in this one, where you have only a little bit of sulfides in the rock, it's actually quite a smaller window. So kind of maybe counterintuitively, even though you have less sulfides in this protolith here, it might actually be less favorable for gold fluid production because you're not consuming sulfides as fast. So what does this mean for the kind of the general picture? The protolith composition really seems to matter a lot. So having a more calc-semi-pelite composition is going to drive muscovite reaction to lower temperatures. So you get that fluid that's produced at lower temperatures. At those lower temperatures, you need to have basically a very well-tuned oxidation state in order for pyrite to remain stable until that fluid pulse. So it's basically showing that, there's very specific conditions where you would maximize fluid production at the same time as sulfide consumption. Okay, so can we tie ages to the fluid, the metamorphic path. These are garnets that have been mapped with a laser ablation. So you can see that you have different styles of zonation, and this is one of our storolite zones. So it's a typical subsolidus garnet with lutetium in the core, and you have this kind of a rotational feature in the chromium and other kind of less mobile elements, indicating that this is a syn tectonic with respect to the main fabric here, which would be S2. So that's our typical garnet in the subsolidus zones. Once you get to the OPX zones, it looks a lot different. Everything is homogenized, and you get this recrystallization rim at the edge of this very unhappy garnet. So this is the compilation of the ages. We got 12 samples and 12 isochron ages from this. So in the West, our subsolidus garnet ages are all seeming to overlap at around 2660. So this kind of diagram here shows that all these basically from the garnet to the cordierite sillimanite zone, where all those rocks have similar garnet ages, similar garnet zonation. In the East, it's a bit of a more interesting story. We have all the garnets actually seem to be younger by about 10 million years. So even those from the storolite zone, which have the same trace element zonation, seem to be about 10 million years younger in the eastern Quetico. Now, we only dated the supersolidus garnet in the east. In hindsight, it would have been nice to have some from the west, but the key is that even the two garnets that I showed here, which have very different trace element distribution, are giving an overlap in ages. So even the garnet with the resorbed peaks or the resorbed rims have the same age, and that's basically inferred as a peak metamorphic age in the belt. So I did monazites here to complement it, to get different parts of the PT path, to see the relationship between monazite and garnet ages. So from the subsolidus zones, it's fairly easy. They're a bit small, but they're the backscatter shows that it's just one population. And so when we're dealing with subsolidus, we can measure a lot of monazites, and the statistics should show that they would converge in a normal distribution at the age the age of monazite crystallization. In the melt zones and above, we're getting overgrowths. And basically these overgrowths are like sometimes less than 10 microns. So it's not really possible to target the overgrowths. So we are expecting a mixed age in those samples. So I've shown that you have a couple different overgrowths in the highest grade zones. That's basically tracking garnet consumption, and it's tracking monazite growth in the presence of melt, but I won't get into that too much. So we actually used two different methods due to the availability of the Neptune. We used a triple quad only method, and so that's this one on the left here. You can see that the errors on the monazite is much higher than you get on the multi-collector, but because it's a single population, we can use a lot of samples to come up with an age that is not reasonable. Okay. So that's the compilation of the ages. Again, the monazite seems to be systematically a little bit younger than the garnet, so monazite is included in garnet, so that makes sense. It's forming earlier in the sequence. But even if you go to the east, that same sequence seems to be actually offset by 10 million years. And so this is just the kind of the summary slide here. We have a main COHS fluid pulse at 2680 and 450 to 500 C. This is basically a pre to syn D2 event. And then you have a secondary pulse near peak pressures of 6 kilobars at around 500. This is about the storolite in, but this is an H2O, an H2O pulse. And then this heating decompression probably happened quickly after that, and that seemed to be an eastward propagating feature. And then we're achieving the highest temperatures in the belt. So I'll end there, and thank you, everybody.